I didn't do it.
Oh, I think I did.
I didn't do that.
Those are mine.
Yeah. I didn't do it. I know he won't do that. He goes to those others.
I know.
This is an academic conversation. It's supposed to be fun. I got out of break, but I think it's great. Just like I was at use.
Yeah, making it bread.
I was like 8 to
See, the tables are perfect because you have snacks.
right now.
So let's sort of get going for today. So on Thursday, we talked about ordered pairs, we talked about graphing and just sort of that idea of X's and Y's have some sort of relationship. We don't know what that is, but they pair them together in ordered pairs, and then we can go graph them if we want to. So today, what we want, or actually not just today, what we're going to talk about this week is what's called relations, and we'll also talk about functions, but really just relations. So I've given you guys 2 examples of relations. And so notice that. So give me, I guess actually better way to start is kind of give me your thoughts. And I think this is one of the questions. So what is a relation? If these are 2 examples of relation. It's on the reading assignment. What would you say a relation is? A set of ordered pairs. Good. A relationship.
Because they correlate to each other.
And say it again.
They correlate to each other.
I won't talk about that. So the interesting thing is they'll have some sort of correlation, but it's not always the same. So sometimes it is one goes up, one goes down, sometimes one goes up. There's some sort of relationship or correlation. So let me kind of hone in. So the official definition is it's a set of ordered pairs. So the first thing to kind of notice here, I have these kind of squirrely brackets here. Putting these brackets around the ordered pair. So on Thursday, all of these were ordered pairs. So they were just a bunch of points floating in the wind. But once I put these little brackets on it, then these brackets, so then I call it a relation basically. So it is, they say a set of ordered pairs, but the best way to think about it is it's just a group. It's a bunch of ordered pairs together. And I put them together because they have some sort of relationship. They have some sort of reason that they're together. Now, like we were talking about Thursday, I still may not know why they're together, but I am saying they're together in a group. So I call these squirrely brackets because I don't know the official word for it. But also because, so I was telling the other class, for me, in any college class I was ever in, history, sociology, any science, any math class, I could never really connect with any of the official vocabulary that they give for any of those classes. And so what I'd always do is just basically make up my own words for it and just make my own connection for it. I kind of encourage you guys to do that. So as we're kind of talking through some stuff in this class, I'm going to give you guys vocabulary. I'm going to give you these symbols that mean a certain thing. So really quick, just know that anytime humans get together and study something. So one of the things we do is a bit like we were talking about on Thursday. So we have ordered pairs because we need to be able to communicate these connected values to each other, right? So at some point we say this is a symbol for that. and the X's are on the left, the Y's are on the right. So the same thing with anytime human study stuff, we come up with symbols, we come up with official vocabulary for stuff. It's just about ease of kind of communication. The thing with vocabulary though is, so if you're studying the thing, if you're studying psychology, then the vocabulary makes sense. If you're not studying psychology, then it's gibberish. So most classes you're gonna go into, especially the first 2 years of college, you're not studying that thing. So that vocab, the official terms is gonna be gibberish. So what you always want to do is you want to replace their official term with what you want to figure out what are they really trying to say, and kind of replace their term with that, because that'll automatically connect you to the thing and get you to remember it. So I don't know what these are called, but I call them squirrely brackets because that's the fun that makes me remember. Good. So sets always have the little squirrely brackets around it. And it's also my signal as a reader. This is a group, in this case, of ordered pairs. And like somebody mentioned, I mean, we may not know why they're together or what the correlation is. But we'll spend the rest of the class at least trying to figure out some of those answers. So, good. Once I have a group, a set of ordered pairs, there are a couple things that I can ask about it. And so let me write first. And again, you saw this a little bit on that reading assignment. The first thing is domain. And what is domain? The X values. So the domain is just, it's not just a list, it's actually the group. It's a set of all the X values for whatever relation you're looking at. All right. So for this first relation here, what is my domain?
-2 to 4.
So is it -2 all the way to 4, or is it certain? So this is actually a really good point to bring up. So is it -2 all the way to 4, or is it certain numbers? Certain numbers. So it's honestly like a really, really good point to bring up. We're gonna see this. So we're gonna talk through some of this today, and we'll talk through the rest of it Thursday. That sometimes the way the relation is given, it is saying all the numbers from -2 to 4. But sometimes they're just telling you specific numbers or things. Here, they're telling us specific numbers, like y'all said. So a -2, a 3, a 0, 4. So for my domain, all I'm gonna do is I'm gonna put my little set bracket, my squirrely brackets, and I'm gonna write these down. -2, 3, 0, 4, and that is my domain. Since I'm listing out, since it isn't everything from -2 to 4, it's just certain numbers, you have to use the squirrely brackets. That's the way we show us like a group of objects. Main is just all your X values. What about range? What is, say it again.
Values.
Range is then all your Y values. So again, just fancy names for simple ideas, really. Whenever you hear domain, don't think about the word. Domain means all your X values. Range means all your Y values. What's my range here? -1. Yeah, so I'm here. 4, -1, -2, 0. Yes, that is my range. Questions? Just the first example, but any questions on domain and range there?
You don't have to list.
Very good. So let's talk about that question. It's a really good question. Do we have to list them in some sort of order? What do you call it? For domain and range, when it's given this way, when it's just a bunch of separate values, no, it doesn't matter the order. You can list it in any order you want. So, we'll see it with some further examples. So there are some examples. There are some, there's just some examples where you have to give it in order, and I'll kind of tell you which ones those are. But in general, one of the things that's kind of So basically in mathematics, a bit like we were talking about on Thursday, where left and right are arbitrary, right? They're just words for this way and that way, and same with up and down. Order doesn't actually matter at all. Mix them all up, you can put negatives before positives, positives before negatives. It really doesn't actually, so in mathematics, truly order doesn't matter at all. The only reason that you guys on math homework or in a math class ever have to give order is actually because we write things in textbooks. Textbooks are written by authors. Human language tends to have an order to it. It's not the same order everywhere, but it always has an order to it. So the problem is actually that math books are written by people that are writing in language, so they're authors. And so again, I'll tell you the examples where the homework system is going to want things in order, but that's actually the interesting thing. Mathematics, unlike most other human languages, has no order to it at all. So when we write it in textbooks and make homework systems out of it, it's actually one of the problems you run into. It's frustrating for mathematicians because because the order doesn't matter. So you should be able to enter it in any way you want. For the homework, on problems like this, you can enter it in any way you want. And we'll come back. So on the second example, so I wanted to write the second example to make the point of mathematics doesn't just speak about numbers. And so most of the time in this class, we're going to see numbers. But in upper level, like theoretical math classes, you actually rarely use numbers. So a relation is any set of ordered pairs, and an ordered pairs is any sets of objects connected to each other. The objects don't have to be numbers. They could be words, they could be shapes. The little sun that you wrote in kindergarten on your drawings. It really doesn't matter. So this is a relation just as much as the first one is. So what I'll do, I want to give you guys just a minute or two. Go ahead and write the domain and range. I pretty much like to have music on in the background of. So does anybody have trouble working? Occasionally somebody does. So just while you guys are working, I'll put in the playlist. And yeah, it was that two track. Yeah. So that automatically, like, if you filled out that form, it automatically. So yeah, I have to calculate it, I just see it written. So I'll bring you. But you're saying. I do. Yeah, I have it. So you don't have to worry about it.
I'll have to go for the running right there. Well, I'm gonna park and get a wing. No move. Player.
You don't know. It's actually just put in a calculator.
Yeah, there's no quarterback gets one. Very,
Like 6 months.
The Eagles were gonna play defensive players, so.
Yeah.
All right, let's see what y'all got on this.
Is that a G?
That's an A,
Oh,
badly written A. What'd y'all get for the domain?
Be the.
an A.
So. And what about the range?
Where we triangle, square, and so.
Yeah, I did do that.
That would be the domain and range here.
It was just.
Yeah.
Yeah, good question about repeats, so you don't have to give repeats. You technically could write it if you want, but why spend time and energy that you don't need to? So when I have a group of things, I just need to label what the things are. I don't need to label how many there are of them. There. There. Alright, so one way that they'll give you relations, because a relation is a group of ordered pairs, you'll see it like this, where they just physically write out all the ordered pairs. However, that's not the only way we'll see them. We'll do it one at a time. Alright, so this is another way that you'll see them give you a relation. What they start trying to do, like we're a little bit like we are talking about on Thursday, so graphing is a way for us to turn numbers in our conception of a visual. So they will slowly turn these ordered pairs more visual. One way to do this is a table. Let's maybe then manage the table over just writing out the order pairs like this.
You can easily see all.
Yeah, you can easily see all the numbers. So the funny thing about this is that honestly, this is just a visual trick we play on ourselves, right? Because all I did is replace parentheses and squiggly lines with rectangles. And suddenly we can easily see it, and we can see the connections very easily. We know that, at least we've been conditioned that if they're in the same row, these are my X's, these are my Y's, then we automatically see that if they're in the same row, they're connected together. That's exactly it. It's a very clever visual trick that we play on ourselves. It really helps us see. But it's just another set of order pairs, another group of order pairs. So same deal, y'all can tell me the domain range there. So I'll give you a couple minutes. What are you looking for the domain? And that's the nice thing about this, it makes it completely visually, really don't have. What about the range? It's on ones. So -3. Another way that they're gonna give you, another way that they're gonna give you relations, so that's what we do. They call this an arrow diagram. Mathematicians are not clever, and we often name things pretty depot, pretty basic. So this is an arrow diagram. Again, also a relation, I'm showing you connections between cities in Texas. In this case, it's basically their professional sports teams. But that's an ordered pair. So notice I'm going even more visual with this, with an arrow diagram. Now it's not even rectangle, it's drawing arrows between things that are connected to each other. But it works just as well. What do you call it? I honestly don't see this as much. So if I wrote my own college algebra textbook, I would actually write a lot, like you'd see a lot more of these. Because in higher mathematics, you see this a lot. Arrow diagrams are actually crazy useful. And for some reason, everybody would be like, all candidates just kind of decide if they don't want to play with it, but it's actually really, really useful. Thanks. But this is a relation just as good as the other ones. Let's just do this as a class. What's the domain?
Antonio Dallas, yes.
Target Dallas Houston. Or just, yes, just our X's. My range.
From Mavericks, Astros, Spurs, Cowboys, Texans, Rockets. They got smart, bro. They're like the fucking- If you drop the ball, I'll make it.
Next way that we're gonna look at a relation, so just again, a group of ordered pairs. It's just like we saw in Thursday, so if I have some ordered pairs, I can just grab it. Right? So that's the ultimate, like again, we're slowly taking this from completely numbers, symbol representation. More of a picture, now let's just do the.
Three quarters and ball, like mine.
So I could give you. This is a bunch of ordered pairs. This is a group of ordered pairs. This is also a relation. So same deal then. Like we were talking about Thursday, the nice thing about this is as long as you can, as long as I space this out pretty largely, or you have some grid lines you can read as well, then you could just read the numbers straight off of it. So same deal, I'll give you guys just a couple minutes to write the read range there. I'll say for the definition.
Yeah, it's not even. Those things.
What about range? Again, we don't have to have them in order, but I will say usually once we get relations that are graphs, so once we hit graphs. Because of the way our mind works, we like to take things visually, we usually like to take things in order. Left to right, on the top, top to bottom, whatever. So you'll find that it's actually probably easier for you to spot the numbers if you do take some direction. I mean, it doesn't matter the direction you take. Selection went bottom to top. It's much easier. Yeah. Right, so before we get to, so there are some, there's some other graphs that I want to look at. And then there's one other way to represent relations, which is actually with equations. And we'll get there probably Thursday. But I want to go back and on all these relations that we've got so far. So we've been answering domain and range. So that's the first two things they're going to ask. What they're also going to ask though is whether these relations are functions. So we want to go back and look at what do they mean by that? What there. A second. Let me kind of just talk about where this idea of function comes from. So this is another, I hope at least, once you see where it comes from, it just makes sense what they're looking for. It'll make sense in every situation. So these are all relations. Modern mathematics was invented. The reason it was, I won't say invented, but the reason that they kind of started writing it this way and kind of codified it this way wasn't actually a pure study of mathematics. They were doing it in response to trying to figure out physics, chemistry, trying to figure out, electrical engineering, stuff like that. They were doing it sort of in response to, from about the 1600s on, sort of our modern approach of science. And so I want to talk about, so one of the interesting things about our modern approach of science is there's a way that science works that that studies the universe. So we'll talk about that, and then you'll see that's kind of what we'll talk about. So modern science, we study the physical universe, and we set up experiments. So all modern science is based off experiments. Somebody gets a hypothesis, a guess, about if I change some situation, what's going to change? So literally, modern science would set up an experiment where we know baseline that A produces B. What I want to figure out is if I change A, if I change the cause, what happens to the effects? And so what we'd like to see is, let's say I changed A to C, and I want to see the effects. So basically all of modern science is based on sort of this idea, this assumption that we have that if we change causes, we change effects. So just sort of the idea of cause and effect. And this is what I'd like to see. So what makes science work really well for studying the physical universe is, for the physical universe, most of the time when you change the input, you change the output. And so then what we can do is we can go and look at how did I change the input, and why would that affect the output? Why would that cause the change in the output that I look at? I can do repeated experiments and make guesses and kind of confirm those guesses. However, so the idea of change, or just this concept, you change a cause, you change the effect. Is that the way the whole universe works? What do you guys think? So philosophy science question. Not even really science, but just philosophy question. Is that the way, is that your experience in reality?
Yeah.
So I'm hearing yeses, I see a head shake. What do you guys think? So I want to challenge you guys then, because I would actually say that that's rubbish. That's actually not the way that a lot of the universe works, or at least that's not the way parts of the universe work. So definitely a lot of times like physics and chemistry. But let's say in your everyday life, you're in some social scenario and you do the exact same thing you like two social scenarios that are the same. Somebody says something, you react to them the same way. Do they react the same way every time? So honestly, people muck the universe up. So like oftentimes you do the same thing and you get a different result, even from the same person. Even the same person will give you a different results with your inputs, your emotional, conversational input being the same in the same scenario. And so when that happens, does that make sense to you, or is that hella confusing? It makes sense to you? Okay, then you should study psychology and sociology because honestly, I mean, I think, what about for the rest of you guys? Does it sort of make sense to you? Like, okay, then you guys are better than me. So this is what, maybe I'm probably like borderline autistic / Asperger's. This is the shit that drives me crazy in life, that you do the same thing and you get a different result from people. So I can't figure it out. I still can't figure it out in most social situations. So, okay, but it makes sense to you. It's actually good. So you guys are gifted, more than me. There are also other situations in life where, say, A gives me B, but also C gives me B. Doesn't change the outcome. So I changed in cause, but it doesn't change the effect. So modern mathematics was built to deal with either that first scenario that I gave you or this scenario. At least I want the causes to change. I don't want repeated, basically, causes or repeated instances. And let's say I change the cause and it doesn't change the effect, that's still something I think why doesn't it change the effect? Modern mathematics and science, though, doesn't do well with this scenario. Doesn't do well with no change in the cause, but suddenly spontaneously I get a change in the effect and the outcome. And that's actually when you have situations like this, which comes up a lot in life, especially dealing with basically elements in the universe that act irrationally, with humans dealing with things that are not. That's why the social sciences, they use statistics. Statistics actually helps us deal with situations like this, where the same input gives us different outputs, so we can sort of codify and figure out how often do I get one output, how often do I get another output, what should I expect to get out of that situation? What percent of the time am I going to get this, or what percent of the time am I going to get that? So I'm saying all that to say this situation do not like to deal with it, because algebra doesn't do well with that statistics. So this situation, if I wrote this, there's an arrow diagram, so I have an idea what this means. If I wrote this as ordered pairs, what would the first ordered pair? Ordered pair. So A produces B, what ordered pair would that be? A comma B. What about the A produces D? What would that ordered pair be? So this situation in mathematics, we say this is not a function. So a function basically is something where I don't have one cause gives you two different effects. And the tell is that you have repeated x values. So if you see repeated x values, that means the same input is giving you two different outputs. And so that is not a function. And so what we'll see sort of beyond this week is that in algebra, we only deal with functions because we can't analyze, algebra can't analyze things that are not functions. So we're gonna spend this first week just doing a little bit of identifying, is it a function or not, so that you know which ones we can work with, which ones we can't. So that's the tell you're looking for, is repeated x. So I want to go back to all these examples I gave you then. So going back to number one. So then what they're gonna do is they're gonna ask you, is this thing a function? And it's a yes or no question, but you also gotta explain kind of why your answer is what it is. So what do y'all see here? Is this a function or not?
Yeah.
And why is it a function?
Yeah, but it has one out there.
Yeah, every input has one output. Now, I will say that, so let's talk about that reasoning. We're gonna talk about something on Thursday called a one-to-one function. So every input having one output is actually a one-to-one function. Well, no, actually, the way you said it works. Never mind, sorry. Yes, so every input has one output that says the same thing as no repeated x values. That's okay. So this is function, no repeated x values. Or every input has one output. What about number two? It's not a function because why? Yeah, and when you're given the reason there, so yeah, there's a repeated x value. I do want you to give the specific, at least, whichever one's repeated, or at least one of them. So which one is repeated here?
Right.
Oh, the is repeated. So for every relation, I can go through and analyze, is it a function or not? And that's all I'm looking for, repeated x values. So what I'll have you guys do is all of them, so 3, 4, and 5. Go ahead and take a little time and answer the same question. Are they a function, yes or no? And then give me the reason. Okay.
It could be both ways.
Oh, sorry.
Like if you put a line.
Okay. Okay, no, you're good, no worries, yeah. I'll have to look at it, see who- Okay, I was gonna say, see who are your impression, yeah. Well, no, it's not, except so for the final will happen. Sort of like. It's all. For face to face. So it's all, so you're just in class, it's all in class. You're gonna right now. Everything that you're doing. So. Well, like I said, because, so this, I copied this over in class that we're, I would take colleges.
Someone must be.
Let's see what y'all are saying on these. So for number 3,
Function.
so it's a function in Y.
Oh, because the X values don't repeat.
So no repeating. So this is again. Then what about 4? Yeah.
So if like the Y values, repeat, it's still a function.
Good question. Yeah, so if the Y value is repeated, it's still a function. So we are only worried about the causes or the inputs repeating. Yeah. Any other questions on 3? Or so what did you say for 4? Function or not? And why not? Because Dallas repeats, Houston repeats. So again, remember these arrows are just showing you visually the other things. So Dallas was creates Mavericks, Dallas also creates Cowboys.
Oh, dude, I got that right.
Not a function.
No, it's. Oh, it's here.
All right, and then what about 5? This is also not a function. What repeats there? Say it.
It is a function. Is it?
Yeah, negative, but negative 2 don't repeat it. So you have -2, -3, you have -2.
It's like if it's very well.
For mine, it just looked like -1, but yeah.
Yeah, so this is the -1. Yeah, so, and, but what?
Oh, it doesn't look like if you put a line directly in the middle, it doesn't look like a,
Okay,
it'll be like a.
yeah. So you're saying
It won't
if
be,
you put a
it won't be
vertical
like a
on,
whole number.
yeah. Yeah, so that's fair. I mean, so I will say on these graphs, especially the ones without grid lines, assume that it is like whatever whole number it's nearest to. Yeah,
Okay.
but that's fair.
Okay.
So if it was that, then you're correct. So,
No, that's not a function. It's 2 x's. You already know about it. Look, you see the dot right there. You see the lowest dot? The highest
all
dot?
right, then let's continue with some more graphs.
X. They're both measured to No. You should have done some usage on like those. Yeah.
So still a graph, but notice this time I don't have separate points. So a little bit of code. If from geometry, one of the key ideas is that if you have a line like this is actually an abbreviation. What we're trying to say is every point from here to here, sort of along that direction. So some ways the way you want to think about it is every bit of ink is a point. And if every bit of ink along this line is a point, first of all, how many points do I have this? Actually, so, it's a lot, it's actually infinite, but so that's the first thing to notice here is, 5 I had 1, 2, 3, 4, I had, yeah, give or take. So 7 points there, I had, however many. 4 on 3, all my examples have been some sort of, like I could count how many there were, they were separate, 3 of them, 4, 6, whatever. This is the first example where we're gonna run into where so one of the reasons they run it this way is I actually can't physically write out all the ordered pairs. Because I'd have to write out an ordered pair for every bit of ink along this line, and that's impossible. But I'm still trying to represent that. I'm trying to say every single element here. So then if I go and try to describe or write the domain. So if there's an infinite number of points here, I couldn't even write the ordered pairs out. Am I going to be able to write the domain? I would have to write every number. So first of all, what's the x value here and what's the x value here? Okay, that's -3. 2. I literally have to write every possible number, not just whole numbers. Every single decimal, all the little square roots and stuff. I have to write everything, which is physically impossible to do. So when you get a situation like this, and they're still going to ask you for the domain, then we're gonna try to write what we just described, all the numbers from -3 to 2. But we have to write it a different way because we can't physically write them all out. So instead of writing them with these little curly brackets that I've been using, when you get a situation like this, you have to write it with what's called an interval. Since we can't write everything, we're going to basically just say abbreviation. I want to just say every number from -2. So the way I'm going to say that is -3. So I'm going to use the comma now to mean 2. So this is basically literally this comma is my way of saying every number from -3 to 2. But that includes, so this point has an x value of -3, that point has an x value of 2. So instead of these, write these square brackets. Square brackets tell me that I actually have, I reach -3 and I reach 2. Square bracket. So again, I couldn't write out everything from -3 to 2, so mathematicians literally just invented, I mean, it's what we do with language all the time anyways, we invent symbols to mean what we're trying to communicate, right? So they invented this symbology. Give me a guess, and what do you think? Say -2, so the y value here was -2. And the y value there is 4, so yes, we want to try to say the points here would have every y value from -2 to 4. So you're exactly right. So right,
If it was an open circle.
then we'll use parentheses on the open circle. So and not just on the open circle, so that's that's good, we want to talk about. I want to start another example of sort of. So we'll get to the open circle. But we will be back. Something similar. Same 2 points, we don't make it 3. This time. I'm not gonna stop at the points, I'm gonna keep going on. I put these arrows on the end of my line, and those arrows are an abbreviation, it's like having a dot, dot, dot. When you're writing, it just means. It's. Now I wanna try to describe the domain.
Infinity to infinity.
Yeah, so there's actually 3 different ways to say it, but 2 different ways that I think they usually use in books. So let me get to. Let's start with your way of describing it. You said all real numbers. And why do you say that? What does that mean?
It's just like all. Yeah, every single number.
And visually, what do you see that tells you it's every single number?
The arrows really.
Okay.
Unlike that really.
On 6, we had dots that ended at.
There's no limit.
We knew there was a boundary. It only went so far. But the arrows are telling me it just keeps going. So I have to go beyond those points, which means my x values are going to keep getting lower, higher. The y values are getting lower and higher. The x values are keep going farther left, farther right. We cover everything basically. So one way to say this is all real numbers. the way that that I think in this homework they want you to give is the way she was talking about, somebody redoubled. They're still gonna want you to give an interval. And so when we say all real numbers, we mean everything. And so physically, if you think about, let's think about the x values, the x values keep going farther and farther negative. If you keep going on the number, you never stop. What's our word or our concept for that? Yeah, infinity. Yeah, I was just trying to get it. So you got it, yeah. So yeah, infinity is, again, just mathematicians made up, it's really a word, it's a concept for you keep going and you never stop. And if I keep going and I never stop. So my x values keep getting farther and farther negative, so we're gonna call that negative infinity. So everything negative infinity. The x values over here keep going to the right, so it's gonna be everything from negative infinity to a positive. Now on 6, we use these brackets because we, like somebody said, we stopped, right? We reached the value. Do you ever reach infinity? We can't use brackets for infinities. Because we never reach it. So we use brackets for things we can reach. We're gonna use parentheses for things we can't reach. Must be in some situations, that's. But, so things we can reach, we use brackets for things that we can't reach. I want you to notice that this use of a parenthesis is completely different than what we need to use parentheses for. Actually, math is a language, and unfortunately, they use parentheses. They use that one symbol for a lot of different meanings. And we're just gonna see that as we go through the class. It's one of the things that we mathematicians are very logical, so we should have used one symbol. So cause and effects for every single thing we're trying to explain. Is not an overview in the sense to get that in this. There, yeah, because you can list them out, because it's not everything from one number to another, list them out, then you always use the set brackets. Yes, yeah. Good question. But here we never reach infinity or negative infinity, so we're gonna put parentheses on both of them. Range, my y values keep going down, negative and up positive. So that's gonna be the same thing, negative infinity, or you can say all. But I will say, I think this, the homework wants you to give intervals, but. With this, and it also gives me, at least in my mind, a little so this example looks a lot like number 6. 10 to 4. What's the difference? Using this open circle. So they call this an open circle. Again, that's mathematicians not about. But this open circle has a very specific. So you guys wouldn't sort of see the context in a class like this, but often, so like I said, modern mathematics was really invented to service modern science. And when you study, so modern science, when we study a lot of things, especially in physics, and chemistry, this idea we have in six of like, you know, all my results are gonna be from here to here, and they're gonna reach, you know, we have boundaries. That doesn't always happen in a lot of experiments. In fact, I'd say probably 50% of experiments, you don't get, you'll have maybe a boundary on one side, but you'll have some values on the other side that you get really, really close to, but you never reach it. That's what this open circle means. This open circle physically means every point as close as we can get to 2, 4, but without actually ever reaching 2, 4, without that one point. Like I said, it actually comes up a lot in science experiments, and a lot of the laws that they figured out first though for physics. But that's the thing you gotta know is just what it means. It means that you don't reach that value. Which means that when we write domain range, what are we gonna write? We're gonna use a square here for the values we can reach. We're gonna use a parenthesis here for the values we can. So the domain here. What's the domain? Yeah. And then keep going, what's the range?
Make it do a bracket.
We should go back and answer the questions about functions on this. But yeah, so this, on Thursday, when we come back, we'll play with some more graphs. Not one hit and more. Kind of mixing some. Let's go back and talk about whether we do. So to be a function, I'm looking for no repeat x. Go back to 6 here. So same thing. Yes. That's a function. And so how can you tell that there's no repeated x values? So you're exactly right. Okay. Okay, so there's this idea of a constant, but basically it doesn't go straight up. What about for the rest of you? How can you tell? Or describe it in your own way. How can you tell that there's no repeated x values? I just looked at the built-in image. Okay. The one thing that's gonna throw you off on this is the domain and range. So you basically can't look at it like you did for the previous examples. So on the previous examples, they were just separate points. The problem here is, for instance, you know, if you're looking at the domain, it's saying everything from one value to another. So you basically the numbers you see here are all the numbers. Yeah.
If you take a vertical line along the whole x-axis, there's no point that's gonna repeat.
So basically what we want to talk about is, so what they both kind of reference is, if I did have repeated x values, what I would see, so for instance, if this graph had another point, the -3 for the x value, then physically I'd have to see another point somewhere up here. I'd have to see another point above it. And notice that we just don't see that. So there's something called the vertical line test, which is not really a test, but the idea is basically when you're looking on a graph like this, for whether it's a function, you can just look, like she mentioned, and like the vertical line test, you just want to look, do I see points vertically above it? If I don't see that, then I don't have repeats. So if you think about on this graph, if I drop like a vertical line through there, if there's repeats, I would see another point somewhere on that line. But I don't see that, no matter where you move that vertical line. And it's the same for 7 and 8. So 7 and 8. So I don't see you in your mind drop in a vertical line here, drop in a vertical line here. You're never going to see repeats. So all of these, so to save us time, I won't write it out, but all of these are functions, no repeated x values. You can say vertical line test if you want. or you want. Good stuff. We will continue on Thursday. Right, I'll get you back. I guess, never mind, I'm not gonna try to get it. No worries, yeah. So say the name. Thank you. Yes, you're Roslyn, I know. Yes. Roslyn.
Any trick. Nah.
You came.
I'm gonna off his phone. No, she can just-
Do you like, the guy from Wonder Woman?
Yeah, yes.
He's like, "This is not like that." And they compare to live next year. Oh, right. This was.
I forgot to send it over.
Did I just put it on my note? I was like, really? Awesome.
So, yeah, you're gonna start doing, we have the relations and functions, homework assignment and Alex. Yeah. Same playing with it.
I can't sing. I feel like I have a pretty good voice. I just
Yeah.
don't do it. Oh, yeah, but you didn't sing it. Yeah, like my last class, he wanted me to sing and I was like, on the spot in front of everybody.
Yeah.
No way, Jose.
Thing like, usually end up being 5 nights a week, like tonight, it'll be Idle Beer Hall, they have karaoke at 7-11. So, yeah.
Karaoke at like parties.
That's okay, but
Yeah. No, like,
Look who looks better. I'm okay.
I mean.
That crazy. I'm dropping your class.
I mean,
like,
neither of them are necessarily attractive to me, but yeah, yeah, hers is better. Yeah. You have to find the pictures, you gotta have a valid sign it.
He doesn't need to have a shirt on. He does.
Roslyn, what major are you?
Diagnostic medical sonography. Yeah, we have the same major.
Yeah.
That's all right.
Question, yeah.
Anything else?
Is there
Your test. Do you have a?
anything else?
It's fine,
Is that
yeah,
okay?
that's fine,
Okay,
yeah,
should I
that's,
go and like tell them that I need one, or is that?
no, if you have a calculator. You can
Because
use
I
that.
did sign up like on the first day, you know how we had to sign up. So that's why I'm wondering if I should go or just
Well,
go get it.
well, so the thing is, I'm gonna bring it to you guys, they actually,
Okay.
they gave me all the calculators that you guys requested, I just couldn't bring it with me today.
Okay,
Yeah.
sounds good.
Okay,
Just wanted to make sure.
Okay.
Thank you.
you're welcome.